10:30. Thanks everyone for coming. This is Put Some Where in Your Where clause, which I realize could maybe have been more explicitly titled an introduction to PostGIS or an introduction to spatial databases, but I like snappy titles, and hopefully some of you are here just for the cool title. I've had a long-standing difficulty preparing talks for Postgres conventions in figuring out what content is the most likely to be interesting to the largest proportion of the audience. Because when I talk to audiences at GIS conferences, everyone already knows a lot about the potential of spatial analysis for exploring data and the power of cartographic representation for visual storytelling. What they don't know is anything about databases, why they should use them, how powerful the tools are, how their niche GIS software is increasingly irrelevant in the worlds of data science and business intelligence. So I'm someone who straddles the GIS and the database worlds, and as such, hopefully I have something interesting to teach both GIS and database audiences. Hi, my name is Paul. Feel free to put up your hand and ask questions during the talk. We've got quite a long session, so it's unlikely the questions are going to prevent me from finishing. And I find the questions asked in context to the material are usually more interesting than ones that are sort of asked at the end anyways. I work for Crunchy Data as their expert on geospatial software and databases. Third day. I'm a founder of the PostGIS spatial extension for Postgres with their particular specialty in the vector data side as opposed to the raster data or topology. And I've spent a lot of time working with and working on other projects in the open source geospatial world, which are important when it comes to actually putting spatial data into practice. So in order to try and write up this talk, I had to form a picture in my head of who I thought I was going to be talking to, what their background knowledge would be, what they'd want to get out of a talk about spatial data and databases. So I visualized someone working for a larger organization, not necessarily private sector, but big enough to own some large databases of their own, big collections of customers or citizens and sales records, clients, case histories, that kind of thing. An organization with data that could be used with spatial to garner some new insights or add some new efficiencies to the business. And I figured since this is a database conference, I could generally assume familiarity with database concepts. So if I say relation or table or tuple or record, you'll know what I'm talking about. And I figured that since you're here, you have some interest in spatial concepts. And finally, I assume some knowledge of SQL. Later on in the talk, we'll be looking at some examples of spatial SQL. And knowing how things like joins work is helpful when we start talking about spatial joins. And I also use some Postgres-specific stuff, like the copy command and distinct on that I assume you've seen before as Postgres users. So why care at all about spatial data? What's the motivation for taking on all the complexity and extra tooling associated with spatial data? Let me give you two generic motivations and some specific examples. So the promise of spatial data is twofold. The first motivation is a directly analytical one. We can use the power of spatial analysis to leverage information between domains that otherwise might be hard to leverage. So, for example, we can take a table of customers, our own data, and connect it to third-party data like census data and infer things about our customers like their income distribution or educational patterns. We can also take those inferences and apply them back against the source data to mine for effective action. So if you know your prime customers for barbecue accessories also have a certain income, age, and racial characteristic, you can work back to the spatial data to find out which zip codes share those characteristics and send out appropriate marketing info. And how's that even possible? It's possible because spatial is the universal key. In the database world, we're used to explicit keys. Our relational models relate different data sets via explicit relationships. And this works okay when we have control of all the parts of our data model. But what happens when we want to relate third-party data to our data? We end up hunting around for proxy keys, right? We start looking for DUNS numbers, or we thank heaven when we can link things together on zip code. But we often lack those keys. But the good news is geography can come to our rescue. Spatial autocorrelation is so common it can be considered the default state. Or as Walter Tobler put it, more poetically, everything is related to everything else, but near things are more related than distant things. One reason this is so, at least in the field of human geography, is that humans tend to be highly assortative. That is, we tend to cluster together with other similar humans. So, for example, here's a dot density map of Chicago, where each dot corresponds to one person and is colored by their self-reported race in the 2010 census. Dot density maps can be very pretty ways to display maps of people because they simultaneously communicate the population density as well as the variable of interest, and they also communicate mixtures well. So humans in Chicago sort themselves by race. They also sort themselves by income. They also sort themselves by partisan leaning. Note that different variables can have very different spatial distributions, but they all do tend to have patterns where the variable doesn't radically change as you move across space. Near things are more similar than distant things. The variables are spatially autocorrelated. So one motivation for getting into spatial is that using the power of the spatial universal key, we can transfer information between data that otherwise has no explicit linkage. Another motivation for getting into spatial is just the power of storytelling. Just as arranging your data into a chart or a graph can tell a powerful story about trends or proportions, arranging your data onto a map can surface patterns that tell a story the way a table of numbers never can. If I arranged this precinct data into a table, you'd probably not be able to see the obvious pattern in the data. Arranged on a map, practically hits you over the head. Give me a random American and ask me to guess their partisanship, I got a 50-50 chance of getting it right. You give me a random American and tell me how far away they live from the nearest city, and my odds of making the right guess go way up. There's a pattern there, but you only see it when you see it on the map. So arranging data into a map is a powerful visualization precisely because of Tobler's first law. It makes the nearness of things to one another visible and explicit, which in turn allows our minds to see the patterns of nearness between different parts of the data. So as database folks, we're late to the mapping party, and people have been doing maps with computers since the late 1960s. The first GIS system was the Canada Land Information System, which was purpose-built for the Canadian government by IBM. They custom-made all the parts, the data capture tools to turn the paper maps into computer data, the pen plotters to turn the digital data back into paper. And they even did some computer graphics, which back in '68 was some incredibly high-end stuff. The kind of analysis they were doing in '68 are the sort of things that GIS people still do today. GIS folks conceive of the world as a superposition of layers. So we're in a building. It might be part of a buildings layer. It's sited on a legal parcel that's part of a municipal parcels layer somewhere. We're on a hill, or actually the bottom of a hill, that might be part of an elevation layer. We're breathing air that might be part of an air quality layer, and so on. And once your geographic reality is decomposed into different layers, you could apply analysis to these layers individually and then build back up an analytical result by recombining them. So here's an example of analysis that might be run in a lucky GIS shop. And I say lucky because most GIS shops are devoted to data maintenance and display. They keep the database up to date. They print new maps. Old school GIS, as practiced by county offices and municipal city halls, is deathly dull. But here's some relatively exciting analysis. Answer the question, find areas in our county that are suitable for residential development, steep enough, big enough, or sorry, not too steep, big enough, not close to water, not already developed. So excuse the graphics quality. It's an old example, about 20 years old, but it's visually simple enough to make the point. So you start with a layer of land uses and apply a filter that strips out everything that's already developed. And you get a mask of suitable land uses. Now for the water restriction, take that same map and filter out all the water areas and create a mask of all the areas that are more than 50 meters away from the water features. To get the slope restriction, start with an elevation grid, calculate the slope value of each cell, and then mask out all the areas that are too steep. So at this point, we've got 3 Boolean layers for suitable uses. We've got far enough from the water, suitable use, and flat enough slope. If you AND together all those layers, you get these are all the places that meet those conditions. Except we have a condition that areas need to be large enough to be worth developing, so calculate the area of each group, and then throw away all the small ones, and you get your final layer of suitable residential construction areas. And then usually the output of the analysis will be combined with cartography to create an output display product. So layer over the analytical result with a base map. JS people are pretty happy with their layer concept, so they reconceive the technology world as one where layers are the first order concept, and everything else gets attached to the layers. So you might have a database of important information, but what's really important is how it's attached to the layers in the ground. And this is a nice idea if you're a GIS person and if you're organizing your data for GIS, but it's a terrible idea for organizing data in general. So a data model in GIS system would tend to have a graphical spatial representation as the centerpiece. Here's the map, and then each part of the representation might have some extra information tagged to it. Oh, if you click that parcel, here's some things about that parcel. It turns out you can represent that same layer in a more database-friendly way by taking it apart and stuffing the parts into a table. All you need to have is a database that can understand geometry as a type, so that a relation can have columns of type integer or text or timestamp or geometry. Stick that table onto a map, you get basically the same display, but now it's organized in a nice database way, tuple by tuple, row by row. And this is where PostGIS comes in. Because you can do all the analyses that GIS does, but do those analyses inside your database if you can extend your database to understand spatial objects. You need a database that supports type extension, that can store large objects, because GIS objects can be very large. Think about the coastline of Canada, for example. Depending on how tightly you've mapped it, it can be 40K, it can be 100K, it can be 40 megabytes. It needs to index the data spatially, so in a two-dimensional or preferably an n-dimensional space. It needs to support custom functions that can operate on those custom types efficiently. And if it does all that, then you can have geometry in your tables and bring the power of GIS analysis to your database and all the applications that use your database. And that's the best part, being able to take that analysis power and use it in any of the applications that can connect to your database. It's a very generic solution, unlike GIS software, which tends to be a very specific solution. So that brings us to PostGIS. So it's really easy to add spatial object support to your Postgres database. Incredibly easy now compared to when we started. Most of the modern Postgres packagers include builds of PostGIS. So if you've installed from the PGDG yum or apt repositories, you've got access to it. Just yum install PostGIS or apt get install PostGIS. If you're running in the cloud with GCP or AWS, their cloud Postgres builds already have PostGIS ready to run. The same is true of Heroku. If you're building your own cloud or on Kubernetes, the crunchy containerized Postgres also includes PostGIS. Which means that from a database perspective, there's no fiddling around or compiling or finding dependencies. Usually all you have to do to get started with spatial is just run create extension PostGIS in your SQL terminal. The extension gives you 3 new types to play with using the Postgres type extension system. You get a geometry type for data modeled in the plane. You get a geography type for data modeled in the sphere. And you get a raster type for storing gridded data like elevations or weather data. It also installs index bindings to work with those types. So the Postgres indexing system allows new types to bind to the indexes. And the GIST system in particular allows a lot of flexibility in how index pages are constructed and split and traversed. So the GIST index bindings for geometry and geography are effectively R trees in their structure. The BRIN bindings are range indexes. Most of the time, using the default GIST index is the correct way to spatially index a table, but we'll get to that later. And finally, the extension installs over 400 functions that work against the spatial types and answer the kinds of questions that are needed for spatial analysis and processing. Things like, how far apart are these objects? Do these objects touch in any way? Are these objects within a certain distance of one another? So at this point, I'd usually dive off into spatial SQL. And I explained all the kinds of queries you can do, combining spatial types and functions, cool stuff, spatial joins and summaries, maybe some clustering analyses, some processing, generate new geometries on the fly. But my vision for this audience is one of knowledgeable database people who don't have spatial experience, which means you probably don't just have spatial data lying around to use all this fancy spatial SQL with. So that means it would be useful to know how to get spatial data and how to get it into your database. And once you've got it there, how to see cartographic representations of that data. And only then, once you have some of the basic tools for working with spatial data, how to do fancy analyses and queries in SQL. So I hope that's OK. So first of all, how to get spatial data. Spatial data comes in all shapes and sizes. And it's highly likely you already have some in your operational data. There was a GIS promotional organization, I guess it was GITA or GISA, anyways. They used to regularly claim that 80% of all data has a spatial component. That's a ludicrously self-interested thing to say, but it's worth looking at. So only a very small amount of data coming into a database has an explicit spatial component, usually. Very little raw data has coordinates associated with it. Although the introduction of very cheap GPS chips has meant more and more companies can actually generate explicit location streams. So where's that 80%, right? It's lying around not explicitly, but implicitly in the data. The process of turning descriptions of locations into actual location coordinates is called geocoding. And it's surprisingly difficult to do. Depending on the structure of the inputs, it may require natural language processing to determine which parts of each strings are names and what parts are structural. It can involve some very complex special cases. Think North St. Thomas Street in Sault Ste. Marie, or 1235 Street. People name things in the most incredible ways, and it's very difficult to write general purpose geocoding. And it gets more complex because the existence of different components at different levels of hierarchy can guide the parser to make different choices about what component might be at what level. So, imagine Tennessee Street in Lexington, Virginia. And of course, it's possible that any given string might match credibly to multiple physical locations. So any geocoder has to make provision for returning multiple results for a given input string. So it's complex, and it depends on both really good algorithms and quality data with very complete coverage. And it's so hard to put together quality data and quality software for geocoding. There's a flourishing market of geocoding services available online. They all have different software. Mostly they have their own sources of data. Mapbox and OpenCage are very interesting as services that are based on OpenStreetMap data. Google is interesting on being based on data almost entirely assembled by Google itself, rather than licensed from a third party. The Esri service is interesting because it comes from the Microsoft of GIS. Esri is the dominant company in our industry. Apple has a geocoding service, which is interesting. It's seemingly only accessible via their MapKit software library. There's no external API. You can't sign up and hit the Apple service with HTTP requests, but you can do it if you're writing iOS code. And it's not clear if they even provide the service themselves or just white box it. And there are also some open source software alternatives that you can set up if you've got the time and energy to procure the data and assemble it. And that's really where the time usually goes, getting the data in. PostGIS includes a geocoder as an extra extension. If you install PostGIS, you actually got a geocoder at hand. It's called the Tiger geocoder. It's only for the USA, and it uses the US Census Tiger roads data as its source of truth. We find that folks who have a large number of addresses to geocode, so they will hit rate limits or cost limits using the other services, but who aren't too persnickety about the accuracy of the result, they like to bulk geocode on the Tiger geocoder. Polygons is an open source geocoder which uses OpenStreetMap data, open addresses data, and geonames data. So it has completeness issues inherited from the source data. Your jurisdiction might not have open addresses data, so you might not get good rooftop address geocoding. You might end up getting interpolated geocoding. Or you might have poor address ranges on your OpenStreetMap data for your area. So it becomes important to understand the quality of your data for the area you're geocoding when you're using one of those services. That's one of the benefits of using an expensive proprietary service is they generally have full coverage and at least a constant quality across their coverage levels. So at this point, you're probably doing this, and we haven't even gotten through geocoding yet. It's a big, hairy topic. It's a wonder that you can abstract it away. And fortunately, there's a library for abstracting away the problem. There's a lovely Python module called GeoPy that provides an abstract interface to all kinds of geocoders, so you don't have to care which of the 12 different sources are available. You can just stand up ones yourself or use cloud APIs, all of them, and just have one simple API to it. So here's a little geocoding example using the abstraction library to build a geocoding function in the database itself. So we start with a blank database and enable PostGIS. I'm actually going to use my little pgopen database throughout the rest of this talk for running little examples and stuff. And actually all these examples from here on down can be run and work. I gave a bit.ly link. I should probably have copied it in down here. It'll be at the end of the talk as well. That has all this code and explanations of it. So if you actually want to go through and run all these examples, you can run them yourselves. So we enable the Python language, and then we have the preamble to the function. We're going to take in a text representation of an address, any text string, and we're going to return a text representation of a location. And then we can trivially cast that text to geometry in the database. So here's the body of the function in full, 5 lines. We import the geocoder from GeoPy. In this case, we're going to use the nominatum geocoder. This is a handy one because it doesn't require a license key. And it's got global coverage because it uses OpenStreetMap. It's not suitable for production work because it's very heavily rate limited. Otherwise, folks would probably abuse it. And then we geocode our address and format the output into a standard text representation of the geometry, and then return that text representation. And that's it. And then the epilogue. So it's really expensive. Probably cost 1,000 is way too low. It's probably cost $1 million or something because it takes a long time to run because it's a huge web service call. And here's a trivial example at work. My old house in Victoria, Canada. So since the output is a standard PostGIS text format, I can wrap it in another PostGIS function and it gets implicitly cast to geometry and then output in a JSON format. The geojson.io website, very cool website. You can plunk any chunk of GeoJSON in and it will happily put it on a map for you. So I plunked my GeoJSON in and it put my house on the map. So I can confirm that, yep, that's actually where the address is. So the geocoder worked. Probably you don't want to do your geocoding in the database because there's this long back and forth and you don't want to accidentally block your backend on a stalled HTTP request. You might want to write a long-running service. That might be a better choice. Every language seems to have a geocoding abstraction library. So you can just write it once and then forget about it. In 5 minutes, I found a Python library, a Golang library, and a Ruby library. They don't do geocoding themselves, but they abstract in front of the dozens and dozens of possible services you might want to hit. At the other end of the spectrum from data you need to geocode is data that comes with coordinates already in place. Sometimes actual data from GIS software, sometimes just tabular formats with coordinates and columns. I'm going to start filling up my demonstration spatial database by importing a file with coordinates and columns. Now, the US Census publishes all kinds of interesting free spatial data, and you'll probably make use of at least some of it as you get into analytical spatial work. So let's start with the classic data set from the Census, a file of zip code tabulation areas, ZCTAs, also known as 5-digit zip codes. A user on GitHub actually took that file, which is column delimited, and converted it into a CSV file, which looks like this. I need a table to hold that data, which looks like this. So one column for each input in the file, plus a column to hold the geometry representation. The GitHub file is conveniently stored at this URL. So instead of typing in, I made a shortened version. And then I used the Postgres copy command with the program option to actually read the file directly off GitHub and load it straight into my database. I really love the copy command. It's really powerful. I love being able to pipe a file into the database directly from the network. That's sort of like a magical trick. So copied in, it's a CSV, it's got a header. I'm filling in my zip latitude and longitude. The geometry column ends up being null. So the first 3 columns are filled out. To populate the geometry column, I need to update the geometry column. So here's a couple more PostGIS functions, in this case for constructing geometry from reals. So make point creates a point, but without spatial reference information, and set SRID adds a spatial reference and metadata number to the geometry. So without explaining why yet, just take my word for it that 4326 stands for latitude longitude coordinates on a WGS84 spheroid, so the one that GPS uses. So now that I have a column with geometry in it, I can add a spatial index to that column. For mapping programs and for spatial joins, the spatial index speeds up bounding box filters of the table. I have to specify using gist in creating a spatial index, or I'll also end up with a standard B-tree index on the geometry, which will do nothing for me for spatial queries. We do have B-tree bindings, but not for building B-tree indexes, really just to support order by and group by for geometries. And while I'm at it, I also index the zip code column, so I can do joins on the zip code. And here's what my table looks like rendered on the map. So those are zip codes in the United States, 1 point per zip code. A surprisingly large proportion of spatial data is just columns of coordinates that can be converted into points. But that's not the only kind of spatial object. There's also lines and polygons and polyhedral surfaces and volumes and curves and areas bounded by curves and others too, but we won't get into those, although they are supported in PostGIS. The most common stuff you're going to see is points, lines, and polygons. The most common GIS data format is a format from the mid-90s, the poorly named shapefile, which actually consists of 3 files. And a lot of non-GIS folks have a strong reaction to shapefiles. It's like, magic GIS files. We don't know what's in them, and we're very scared of them. It's really important to note that a shapefile is structurally, like in terms of the data in it, is exactly the same as a database table with a geometry column. That's all it is. It doesn't matter what the files are. If, structurally, logically, it's a bunch of tuples. Each tuple has one geometry column and a bunch of other columns with information about the geometry. That's it. It's not scary stuff. It's just like a table. It just happens to have a funny format. So I'm going to go back to the census well and get a zip code tabulation areas again, but this time the actual areas instead of the points. They are distributed as a shapefile, which is to say a zip archive containing a whole bunch of files that together form the shapefile. Every shapefile has 3 mandatory files, the SHP, which holds the geometry bit, the SHX, which is an internal offset index, and a DBF file, which holds all the other column information. This particular layer also has 2 other files that are useful for data loading. The PRJ file includes a text description of the spatial reference projection the geometry is in. And the CPG file includes the code page for the text in the DBF file. So this is important if the data includes extended character sets, accented letters, Asian characters, things like that. This is what the context of the PRJ file looks like. It's a special format for projections. It's called the well-known text form. In this case, it's describing an unprojected longitude-latitude coordinate on a spheroid that's practically the same as WGS 84. GRS 80 and WGS 84 are pretty much interchangeable. There's a couple ways to convert a shapefile into a database format. PostGIS ships with the shape to PGSQL command line utility. It takes a shapefile as input, and it produces a text stream to standard out as output. And that stream can then be piped straight to Postgres, or it can be saved as a text file loaded later. So here's the call to convert the zip code data. We specify the spatial reference ID again, and we're using 4326 as the magic number. I want to have the data spatially indexed. So I use a flag to avoid having to type in create index by hand later. I want my load to go fast, so I use the copy format instead of insert. That's the -D. If I don't specify a table name, I'll get the shapefile base name back as a table name, which is kind of ugly. So I add a base table name. And finally, rather than writing the output to file, I just pipe it straight to PSQL. So PostGIS ships with a tool for shapefile loading. It's fast and efficient. It's relatively simple. There's even a GUI version that some packagers build. But shapefile is only one format, and there's a whole zoo of potential GIS formats or databases you might run into. So what's a poor database person going to do if they're handed some crazy GIS file like, here's my geodatabase file. Here's my map info file. What are you going to do? If you're going to be really serious about ingesting GIS data, it's worth spending a little bit of time to learn about the Google library for format conversions, because it handles all the formats you're likely to run into. And it can also convert between spatial databases and online spatial SaaS platforms like Carto or ArcGIS Online. The Google library ships with a command line tool called OGR to OGR. If you're in the RPM world, you probably get it by installing the Google RPM package. If you're in the Debian Ubuntu world, you get it in the Google bin package. If you're in OS 10 or Windows, you can find builds and download options at the google.org website. OGR to OGR takes as input any of the common formats it supports and writes as output any of those formats. So it's a wonderful end-to-end universal format library. There's lots of apps that use Google as a pipeline to the formats it supports. So they say, I support a million formats, but actually they're just binding to Google. You can write your own ETL system on top of Google if you want. You can use Python library bindings to the C side. Or, simple thing, it's just you can use the OGR to OGR command line tool. You script up an ETL process. Like the command line in combination with what Google calls virtual formats is sufficient for most ETL processes. So here's an OGR to OGR version of loading my ZCTA shapefile again. I specify an output format, Postgres. I'm loading a shapefile with multi-polygons in it, so I specify a multi-polygon output type. Again, I provide a table name to avoid an ugly default. I provide a Postgres connection string. This is a very simple one because I'm doing it locally and I don't have to do passwords or users and stuff like that. But it's just a standard Postgres connection string. And finally, I provide the input source to read from, which in this case is just the shapefile. So my shape conversion used 3 command line parameters. Here's the whole extremely unhelpful help output for OGR to OGR. This is what you get if you type it without commands, without parameters. It'll say, here's how to use myself. Figure that out. The online OGR to OGR web page is much more helpful. And before starting to script up your own Python ETL scripts, it's worth taking the time to read and understand what OGR to OGR can do just as a command line utility, because it can do almost everything you want. It's just that what it can do is hidden inside these 75 command line parameters. So at this point, having loaded a couple spatial layers into my spatial database, you're naturally curious about how we can use the database to answer pressing questions in social science. Certainly I am. And honestly, while finding the nearest coffee shop is a pressing question that almost always gets trotted out, and I'm going to trot it out, many really interesting questions can be addressed if you mix social science data into your system. So again, go back to the census, but this time the non-spatial part. The American Fact Finder is where you can get all the really interesting demographic data. And it provides that data linked to different census geographies, very small geographies like blocks and tracts, up to higher ones, counties and states and so on. Generally speaking, you want to use the smallest geographic element you can get, because then you get the most granularity. In this case, I went for zip codes because they're slightly larger and easier to deal with, but for the analyses, I probably should have gone for tracts. For this talk, I downloaded data on income. The talk notes have the explicit instructions, which are annoyingly complex, but the raw data are available for download. So you can get it down as not as a CSV file, but as a funny column-oriented thing. It's they come in a form that's quite hard to read. The census deals with thousands of variables, and each variable column name tends to be really, really terse, like a 9-character thing. So I wrote up a little script to drop the unneeded columns and add full variable names to each column. The script's part of the notes as well. Suffice to say, without getting too deep into the weeds, I built a few attribute tables for interesting analysis. Here's one that joins the ZCTA zip code polygons to a measure of wealth. The percentage of families in a zip code that have a $100,000 income or higher. And that's what the table looks like for San Francisco. This is the table viewed as a choropleth map. So a choropleth is a map where the color applied to the geometry shapes is indicative of the underlying value. So in this case, deeper green means a higher percentage of families with a $100,000 or more income in that zip code. So you've noticed I've started to sneak in visual representations of the tables that I'm working with. So just like charts and tables are indispensable when you're working with ordinary data in a database, the map view is kind of a necessity when you're working with spatial data in PostGIS, which brings us to the viewing of spatial data. There is no silver bullet answer to viewing data in a spatial database. The simple solutions often lack important functionality. The complex solutions tend to be really heavyweight. But let's start with the tool I've used to create all the maps in this presentation, QGIS. QGIS is a full-featured, open-source GIS desktop software package. So it's got all the strengths of desktop GIS in terms of having features and point-and-click accessibility. And it's got all the weaknesses in terms of having a heavyweight user interface and difficulty integrating with web-based workflows. For my purposes, though, it provides a quick way to see database layers, to apply common stylings like choropleths, and to overlay them on a backdrop for context. So it's like a lot of desktop GIS programs, QGIS is buttonrific. It's got a button for every purpose and a whole bunch of other buttons hidden in optional panels and a further set of context-sensitive buttons that appear and disappear as needed. That's not a great environment for lightweight work, but it can handle really complex analytical problems and the creation of compelling cartography and complex cartography. You can see from the data manager, QGIS is a very substantial integration environment. When it was first written, it supported only PostGIS as a data source. It now supports many, many different databases and formats. It's good for exploratory work, but what if you're trying to build out enough infrastructure for your web developer teams, shown here, to put together web applications with maps? So just very quickly, so you know the prominent options available without really going into how you put them together. It's nice to know what the pieces are, though. Here's two architectures. One architecture is to generate output formats using the PostGIS functions as GeoJSON, as MVT, or as tiny well-known binary. So you basically spit out the literal representations and render those output formats on the client side using a map that can handle those formats. So a leaflet map, an open layers map, or a Mapbox GL map. And these are all web-side components that you can put into your web page. So it's a very lightweight infrastructure. You just have a web page on one side and the database on the other side, and a very thin slice of middleware in whatever language you like, speaking HTTP. So it's easy to put together, easy for devs to understand. The cons, it's easy to crush it if you throw enough data through the pipe, because the client-side libraries will eventually say, you're sending me too much data, and the map will get slow. The other architecture is to interpose a web service between your web map component and the database. There's some upside to using a web service software. The service can perform the rendering server-side, so you can handle much larger data sets. It can also expose a uniform interface to the features, so you can avoid a lot of wheel and API reinvention on the server side. Inevitably, when you write the simple thing that just has a small middleware, you end up building things in your middleware, and before you know it, you've actually built one of these by mistake. You might want to use one of these that already exists, like a map server, a GeoServer, a MapMic, to do your rendering and expose HTTP APIs. The downside of having a custom middleware, or not a standard middleware like map server, GeoServer, is that you've got another thing to run and another piece of software to understand. So that's the web-based side. Before I move on to analysis, I just want to remind you that visualization, it's probably the most powerful trick available in spatial. I really like doing the numbers and the analysis, but the reality is a powerful visualization trumps all of that. And that's one of the reasons why I keep putting maps up, because I'm boring. and maps are interesting. Like something even as simple as point visualizations, right? These are points, but I'm not doing them as dots. I'm doing them as what? Envelopes. Lots of options. Special markers, heat maps. You can do gradient visualizations. You can do isolines instead of doing a whole bunch of points. You can use point clustering, to show larger point fields. And that's before you even get into things like directional vectors, if you have like wind data, other cool tricks. There's so much stuff you can do on the visualization side. So this is where you're using a tool like QGIS. Basically, any kind of visualization you can do in other tools you can do in QGIS, and you can interactively play with them in QGIS. So it's a wonderful tool to get a feel for how you want to visualize your data. And once you decide on that, maybe you then trot it off to the website and say, okay, we're gonna do our cartography like this. Okay, so we finally made it to the best part. I would have started here because I'm a spatial SQL addict, but for a database audience, it makes sense to cover some of the preliminaries of GIS first. So anyways, there's a rule that any spatial analysis talk has to solve the pressing problem of finding the nearest Starbucks, ideally, efficiently, and scalably. So to do that, we'll start by retrieving the locations of all the Starbucks outlets. You've seen me do this trick before, so take it as read that I'm slurping in a table of all Starbucks locations in the USA from the Socrata open data site. And after the table is loaded, I once again add a geometry column, fill it with data, and create a spatial index on it. So we're ready to go. Spatial applications inevitably make some kind of appeal to distance within or nearest. So let's start with a static analysis of the Starbucks data set. So for a point of reference, we'll use Pike Place Public Market, which is the site of the original Starbucks location. A real application might use a cell phone handset geolocation or a map click from a user, or maybe a proxy lookup source of information like a zip code or an address converted to a coordinate by geocoding. So this query fetches the 5 nearest Starbucks locations to the Pike Place Market. The part in blue just constructs a point from the coordinates. So again, we're setting the SRID to 4326, which is WGS 84. In the target list, we're using a PostGIS function, STDistance, to calculate the distance between each returned geometry and the Pike Place point. And the magic part at the bottom, so I don't know what to call this operator. This less than dash. I've decided to call it the TIE Fighter operator because it looks like Darth Vader's TIE Fighter. So the TIE Fighter operator just returns the distance between the operands. Probably it's more correct to call it the distance operator because that's what it returns. It returns the distance between the operands. But when you call it in an order by context, if there's a spatial index, it will actually do an index-assisted ordering by distance. So it won't scan the whole thing and return the distance. It'll actually walk the index and find the 5 nearest things incredibly fast. So here's the 5 nearest. The nearest, unsurprisingly, is Pike Place itself. But what's going on with those distances? What are the units there? That makes no sense. What's happened? And so here we get to our first quirk. PostGIS includes 2 types for modeling spatial features I mentioned off the top, geometry and geography. And they have different capabilities and different pros and cons. So when I loaded the Starbucks data, I put the points into a geometry column, not a geography column. And this has implications. So imagine 2 points, P and Q. P is Pike Place, Q is 3rd and Pike. Note that the units of P and Q are angular units. Right? Latitude and longitude are angular units. They're spherical coordinates measured relative to Greenwich and the equator. They're not planar coordinates, they are angles. So longitude is the angle between a point and the prime meridian, and latitude is the angle between a point and the equator. This is important because it means that there's a right way and a wrong way to interpret these coordinates when calculating things like distance. Because there's a couple ways to calculate the distance between these points. On the sphere, the shortest distance between the 2 points is a great circle. And when you work with the PostGIS geography type, you get spherical assumptions. On the plane, the shortest distance is a straight line. And you work with the PostGIS geometry type, you get planar assumptions. So if we use the same function, STDistance, but change the types of the arguments by casting, we should get different answers. So I've got 2 strings here, P and Q. STDistance implicitly cast them to geometry. Here's another STDistance, but I've explicitly cast them to geography. And we do get different answers. The geometry distance is 0.00359 somethings. And the geography distance is a much easier to interpret 277.7 meters. So wait, why do we even have a choice, right? Why shouldn't PostGIS just do the right thing all the time? Maybe it should. But sometimes we want to use planar calculations, like if our coordinates are planar. All local data can be represented neatly on a plane in a local projection. And when you're on a plane, all the calculations are way faster. Angular units are really, really inconvenient to work with unless you have a truly global data set. So PostGIS only has native support for calculations on the spheroid for a few things, for distance, area, and length. All the other calculations have to be done on the plane. Doing things on a sphere has a real computational cost. These are point-to-point distance functions for sphere and plane. And they get run millions and millions of times in the course of a comparison between a couple medium-sized spatial tables. You can guess which one runs faster, right? Planar coordinates are what GIS systems used, and they're what the geometry type uses. And the geometry type was the first PostGIS type. So there's hundreds of native geometry functions and only a handful of native geography functions. So long story short, if your data can be modeled on a plane, if it's not truly global, if you don't own a satellite, if you're not dealing with global data, you should use a geometry type and an appropriate planar projection. And for the first time in one of my presentations, I'm actually going to take my own advice and remodel the data into the plane so I can keep on using geometry. And since my data are for all of the USA, I can find a passable projection. The US National Atlas projection is suitable for the continental USA and Alaska, so I'll use that. It has number 2163. The data that are already loaded in geometry column with an SRID restriction of 4326. So I need to change the type definition and simultaneously reshape the data to match that new restriction. So new type, geometry point, that's unchanged, but the SRID is different. In order to make the data match that new restriction, I'm going to transform it from its current SRID to the new one, 2163. PostGIS includes a one-step method to do that. It's great. Alter table, alter column, using. And once that's done, when I look at the coordinates in the database, they aren't that long anymore. They are planar. In fact, the units are meters. So circling back to my example, the example that started this digression, our calculation of the 5 nearest to Starbucks to Pike Place. We have to make one concession to being in a projected system. Since our inputs are lat longs, the input coordinate of Pike Place is a lat long. Before we compare it to the stuff in the table, which is in the US National Atlas projection, we have to convert them to our local system before using them in the calculation. Otherwise, the query is exactly the same. So we start up, we make our point, but before we use it, we transform it to 2163. And now the distance column makes a lot more sense. The only odd part is the distance to Pike Place is larger than 0. But that's because the coordinate is sourced from 2 different places. The coordinate we're using in our query, we got from Google. And the one in the database, we got from the Socrata Open Data Table. So they are slightly different. So the next common query is finding all the items within a particular radius of a point of interest. And again, the point could be generated on the fly with a GPS reading or a click, but again, we'll use Pike Place. And the query looks very much the same, but instead of the ordering operation, I'm running an STD within filter. And note that I'm not running an ST distance calculation. I'm not saying ST distance and a less than test in the where clause. That would calculate all the distances first, and then test them for being less than the radius, and that would be expensive. Using STD within first applies a spatial index to the problem, and then filters on the exact distance. So it's very fast and it's suitable for joins, as we'll see, as well as static lookups. So here's the result set on a map, because that always looks cooler. Note this is again a QGIS map. I'm being cute. I'm using an SVG symbol for the Starbucks points. Yeah, cartography. Also note that cool radius circle. I don't get that for free. In order to put on the map, I need to construct a circle of appropriate size. That's what the query to do that looks like. Again, I set up my Pike Place point at the top, then use the stBuffer function to convert the point to a polygon of the right radius. And you know, since Pike Place is already part of my Starbucks table, I could do this query a little more tersely as a self-join. Pike Place on the right side, and on the left are the locations we're running the dwithin filter on. Because there's a spatial index, and because we're using dwithin, this executes very fast, although it would be faster with an index on the name as well. So let's do a true blue analytical question. Starbucks can put outlets anywhere they like, right? They can put them in malls, they can put them in streets, they can put them on the tops of mountains at the bottom of lakes. But they choose to put them in particular places. So do these places differ from other places in a systematic way? I'm only going to look at one variable. This analysis could easily be multivariate. So this is the census income layer that I created earlier by joining the zip code polygons, the American Fact Finder income data. And doing this analysis for real would probably involve working with the census tracts, which are a much smaller geographic basis. But for convenience, I loaded up the zip codes. So before getting geographical, I'm just going to do a nationwide summary calculation. This is the baseline, the number of households with income over $100,000 divided by the total number of households. So that's the percentage of wealthy or upper income households nationwide. The question then is, how are the places that Starbucks chooses different from the nationwide baseline? Nationwide baseline, 24% upper income households, wealthy households. So here's the calculation. We start with a spatial join using ST-intersects. That gives us every zip code polygon that Starbucks fall inside. Then we apply distinct on to that relation to strip out double counting that would occur in places where multiple Starbucks are in the same zip code. The relation that comes out of the CTE, then we can just summarize, the same as we did for the nationwide. And we find that zip codes containing Starbucks have 29% wealthy households, so 20% more than the baseline. So no big surprise. It's easier to sell expensive coffee to wealthy people. And this is what the analysis looks like visually. It's kind of hard to tell. This is Ohio and some surrounding states. You can see the cities from the place labels. You can see the urban poverty even, kind of the suburbs surrounding the urban poverty in the middle. It's kind of weird when you start seeing that stuff. Here's all the Starbucks locations laid on top. And so the tendency of Starbucks to fall in the wealthier areas is already visible there. And here's the zip codes returned by the spatial join. So as you'd expect, every one of them has at least one Starbucks inside of it. And these then get passed to the summary, and they calculate the summary statistics. So since we had to strip out double-counted zip codes, it kind of makes sense to wonder, do areas with more than one Starbucks differ from the baseline? Like, do they differ more than the generic Starbucks zip codes? Now, it's a bit longer because I need to count the number of Starbucks outlets first, but you can see the general thesis is confirmed. Starbucks prefers higher income areas. So 31.8 is the proportion of wealthy households in census or in zip codes that have more than one Starbucks in them. One of my favorite tricks when I have in my hands in a larger database is to cross-check data with other references. So checking the precincts that voters are assigned to against the precincts they actually live, that kind of thing. And we have a natural example of that here. The Starbucks table includes zip codes, and we have a zip code polygon file. So we can find all those places where the zip codes on the Starbucks table disagrees with the zip code it falls inside of. So it's a very simple spatial join using the intersects relationship between the zip code polygons and the Starbucks locations, pulling out information from both tables, and only looking at the ones where the zip codes are different. They disagree. So here's a chunk of Denver with the mismatched zip code locations shown in yellow. You can see that most of the cases are border cases. Probably it's natural human error, although potentially an issue in the zip code file. That's the trouble with consistency checks. They require some knowledge about the quality of the sources you're comparing with.
Sorry, I didn't understand the last. So what are these exceptions here? What do the exceptions mean?
So for each Starbucks, we're finding the zip code it falls inside. So that's sort of this relation. And then we're stripping out, so we're only looking at the ones where the zip code differs from the one that's on the Starbucks table.
Oh, okay. So you're comparing data sets.
Yeah, seeing.
So you're seeing that they're
Ideally, they should all be the same, right? The Starbucks should say it has the zip code of the zip code polygon it falls inside. So it's a way of cross-checking the data. And yeah, so as you'd expect, most of the errors are sort of border errors. Although there's some that fall in the middle and go, what went wrong there? So far we've been doing filtering and some joins. We haven't started mucking about with the geometries themselves. And PostGIS is full of functions that can generate new geometries from inputs. So for example, we have all the zip code polygons, one area for each zip code tabulation areas, in fact. Since they're used for tabulation, like for sorting and delivering mail, it's a physical process. It's reasonable to wonder whether the geographic structure of the zip codes is interesting or not. So what would a picture of zip codes look like if we had one-digit zip codes, just the first digit of all the zip codes? So here's a query that merges all the zip code polygons that share a first digit. So we're just doing a union. This is merges all neighboring geometries, and we're grouping by just the first digit of the zip code. So it takes a while to run to merge 30,000 polygons, but it works. And the result is an interesting segmentation of the US. So the West Coast, bounded by the mountains mostly, a New England area, a New York area, a Texarkana area. It's all pretty rational looking. I should have labeled it so you could see what the first digit was. And here's a picture with the 2-digit areas overlaid as outlines. So you can see how the main areas are internally subdivided. Again, it's sort of an interesting mixture of geographic influences like mountains and rivers and administrative ones like state boundaries. So that's been a whirlwind tour of GIS and using spatial data in a database. We looked at how to get spatial data, and if you remember only one word, let it be OGR to OGR. We looked at how to view spatial data, one word to remember, QGIS. And we looked at how to analyze spatial data. So remember SQL and PostGIS. And I think that's my time. So thanks very much. And I'm happy to have any questions, Jeff.
Sure. So I was talking to somebody a while ago about a library called Seagull.
Yeah.
CGAL.
CGAL, yeah, like, yeah, but yeah.
Yeah. And so one of the things they advertised and he was mentioning was
Yeah.
the reliability aspect, which has something to do with the order you're applying all the floating point calculations and whether it's maybe deterministic or maybe means something slightly different from that.
Yeah.
So can you talk a little bit about that and how that relates to PostGIS or how important it is?
It can be important, and in fact, it is possible to generate queries with particular data in PostGIS that don't run through because the computational geometry ends up in a non-deterministic state. Seagull gets around it by applying, I can't remember the correct term of art, but infinite precision math. What is the correct term of art for that? Anyways, rather than double precision, they have unbounded precision for their coordinates. Arbitrary, that's the one, yeah, arbitrary precision. So yeah, it is important, and there are cases where PostGIS will fail. We use a different computational geometry library for most of our work. We use a GEOS library, which is based on double precision. It almost always works, except when it doesn't. The only time you run into the cases where it doesn't is if you're doing something which generates new geometries. So the union buffer intersection functions, which actually do new intersections and create new geometries, will, in very rare cases, go, I couldn't do it. Usually it's enough to very slightly alter the coordinates, like give them a random shaking, and they come out. That is one of sort of the long-term important improvements I want to make in PostGIS over the next couple of years, is to remove the last cases where that happens. It's usually not necessary to go to arbitrary precision to fix that. Talking to some other practitioners, they found that recognizing when you have a failure and then going up to, say, quad double generally kills it off just fine.
Okay.
Yeah.
I got the impression, I don't know a lot about this area, but I got the impression that by performing the operations in a very controlled order
Yeah.
and then keeping track of the error bounds and then handling the edge cases, you could also do it that way without necessarily going to arbitrary precision.
Possibly, yeah.
Yeah. Anyway, so yeah, it sounds like it is something that would be valuable, but is not necessarily important for a lot of cases.
I mean, we do get some people occasionally with cases now, but they're almost all gone. So I'm looking forward to getting rid of the last of them. Yeah.
Actually, we use this PostGIS
Yes.
for clustering. Because so we try to figure out if it's like you use the 2 dimensions, right?
Mm-hmm.
They want to make like 500 dimensions. So it actually didn't support it. Yeah. So how many dimensions?
4, yeah. And practically speaking, some of the dimensions are kind of locked down. We built against what's called the OpenGeo Spatial Consortium Simple Feature Specification, which has since turned into an ISO SQL MM specification. But those 4 dimensions are X, Y, Z, and whatever else you want to be the 4th dimension, usually called measure. Sometimes we use time. If you got X, Y, Z and time, we call it a trajectory. You have a few special functions that'll deal with that. But yeah, it's 4 dimensions is where we cap out. A lot of the code is built to be arbitrary, but for practical purposes, we just said 4 will do.